What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of high memory consumption in large language models, LLMs, caused by the key-value KV cache, which typically takes over 30% of the GPU memory during deployment. The method focuses on reducing the memory consumption of the KV cache by dramatically decreasing the number of cached layers in transformer decoders. By pairing the queries of all layers with keys and values of just the top layer, the method eliminates the need to cache or compute keys and values for layers other than the top layer. This approach significantly saves memory consumption without introducing computation overheads during inference, thus addressing the bottleneck of memory consumption in deploying large LLMs with high throughput and low latency.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by reducing the memory consumption of the key-value KV cache in large language models, LLMs, by decreasing the number of cached layers. The algorithm pairs the queries of all layers with keys and values of only the top layer, eliminating the need to cache or compute keys and values for layers other than the top layer. This significantly saves memory consumption and model parameters. To address the cyclic dependency issue where each token attends to itself, the algorithm masks the diagonal of the attention matrix and uses zero vectors as dummy keys and values for the first token. This method ensures that information from each token can still be incorporated in its computation through residual connections. The algorithm also retains standard attention for a small number of warm-up layers to maintain performance in language modeling and downstream tasks. During training, the algorithm sequentially computes tokens in a bottom-up transformer computation graph, pairing queries of all layers with keys and values of the top layer from the previous iteration to break sequential dependencies. The cross-entropy loss is computed only after the last iteration, and gradient stopping is applied to backpropagate the loss through a limited number of iterations to reduce memory consumption. In forward propagation, the algorithm observes that key values converge quickly over iterations, allowing for approximating key values of previous iterations with a smaller number of iterations. The algorithm can be integrated with other memory-saving techniques like streaming LLM to further enhance inference efficiency. By experimenting with different configurations, such as the number and placement of warm-up layers, the algorithm finds a balance between model performance and throughput. Additionally, the algorithm demonstrates competitive performance in language modeling and downstream tasks compared to standard transformers while achieving significantly higher generation throughput.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the proposed method in the paper include a significant reduction in memory consumption of the key-value KV cache by dramatically decreasing the number of cached layers. This reduction in memory consumption allows for larger batch sizes and higher throughput generation in large language models, LLMs, without introducing computation overheads during inference. Additionally, the method enables parallel training by designing a novel approximate training process, addressing the sequential dependencies that arise due to the reduced number of cached layers. The model achieves up to 32 times larger batch sizes and up to 26 times higher throughput than standard transformers for LLMs of 1B30B parameters, while maintaining competitive performance in language modeling and downstream tasks. Furthermore, the method can be easily integrated with other memory-saving techniques, such as streaming LLM, to achieve further improvements in inference efficiency. The approach also offers flexibility in choosing the number and placement of warm-up layers, allowing for a trade-off between model performance and throughput based on specific requirements. Overall, the method presents a novel perspective on reducing memory consumption in LLMs, offering a practical solution for deploying large models in real-world applications with improved efficiency and performance.
How is the method validated or tested?
The method proposed in the paper is validated through extensive experiments on the llama model. The authors demonstrate the effectiveness of their approach by showing significant memory reduction and throughput improvement compared to standard transformers. They also evaluate the model's performance in language modeling and downstream tasks, showcasing competitive results with standard transformers. Additionally, the authors integrate their method with streaming LLM and show lower latency and memory consumption compared to the original streaming LLM. The integration does not hinder the ability of streaming LLM to process infinite-length tokens. Furthermore, the authors empirically analyze design choices in their method, such as the placement of warm-up layers and the number of warm-up layers, to understand their impact on model performance and throughput. Through these experiments and analyses, the authors validate the effectiveness, efficiency, and integration capabilities of their proposed method.
What results were achieved with this new method?
The new method proposed in the paper achieved up to 32 times larger batch sizes and up to 26 times higher throughput than standard transformers for LLMs of 1B30B parameters. The model also demonstrated competitive performance to standard transformers in language modeling and downstream tasks. Additionally, the integration of the new method with other memory-saving techniques like streaming LLM resulted in further improvements in inference efficiency, showcasing lower latency and memory consumption compared to the original streaming LLM on different cache sizes. The experiments showed that the integrated model could effectively process inputs with a sequence length of 4 million tokens while maintaining stable perplexity. Furthermore, the model performance was comparable to that of Tiny Llama in language modeling and downstream tasks, with almost no performance degradation observed in the model with warm-up layers set to 10. The method also allowed for a trade-off between model performance and throughput by adjusting the number of warm-up layers, providing flexibility in optimizing the model based on specific requirements.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method proposed in the paper include the underperformance of the model in language modeling and downstream tasks compared to standard transformers when all layers are condensed to just the top layer for key value, KV caching. This method breaks the typical pattern where lower layers attend to syntactic information and higher layers attend to semantic information, potentially affecting the model's performance. To address this issue, the paper suggests retaining standard attention for a small number of warm-up layers, which slightly diminishes the memory savings achieved by condensing the layers, but leads to almost no performance degradation. Another drawback is the complexity of the training process due to sequential dependencies created by the top layer KV dependencies for each token, which requires an approximate training method to support parallel training. Additionally, during training, backpropagation through all iterations may result in a large computation graph that cannot fit into GPU memory, necessitating the use of gradient stopping to backpropagate only through a limited number of iterations. Finally, the training process of the proposed model is more time-consuming compared to standard transformers due to the iterative training process, which may be a trade-off for the improved inference efficiency.